let us recapitulate what we were talking about last time. We are looking at the design of band limited pulses that we could possibly use in a digital communication system, and the motivation for that was we are simply not allowed to use pulses which are not band limited. That is one motivation. We must restrict our bandwidth to within the allotted one that is given to us. And secondly, if we don't bandwidth ourselves, the channel will do it for us, and that will be worse because that will introduce, do you remember what? Intersymbol interference, which will be a kind of additional noise into the system affecting the performance of the system. To do this baseband pulse shape design so that we are restricted to the bandwidth of interest in an appropriate way, we developed this model, equivalent channel model for our communication system, which we said roughly could be thought of as consisting of 3 filters. One at the transmitter to shape the pulses, one in the channel which is a characterization of the channel itself, and one at the receiver which could be perhaps the match filter that you might be using at the receiver. And the 3 together, the output of this system is sampled every symbol interval, and then it is sent to a decision making device to decide whether in a particular interval a 1 or a 0 was transmitted, or whatever be the symbols that you are looking for. This very crude model of the channel of the communication system can be represented by an equivalent filter which has an impulse response PT, right? So what we are saying is, if we excite this equivalent filter with a sequence of impulses over here, that is this impulse strain, the strengths of these impulses corresponding to the data sequence of interest that we are trying to send, the output will be another sequence of pulses, now pulses with pulse shape governed by the impulse response PT. Alright? And Nyquist proposed that we must choose these different components of the system such that this equivalent impulse response PT does not exhibit intersymbol interference. And the way to do that would be to choose this equivalent impulse response PT such that it is equal to 1 only at the sampling instant t equal to 0, and it is 0 at all other sampling instants. You remember this discussion we had last time? This, if we achieve a pulse shape PT which has this nice property and which also satisfies our bandwidth constraint, then we are through, because that will avoid having intersymbol interference, which is of primary concern over here. The intersymbol interference will actually be still present, but what is important is that at the sampling instance we will not see it, okay? Because at the sampling instance, while one symbol is going through its peak value, the other symbols will be exhibiting zeros. The response of this filter to other symbols will be 0 at each sampling instant, so that successive symbols do not exhibit any interference with each other. So this was the broad idea of Nyquist, who suggested therefore that one could use this method to design pulses. And what we also appreciated was that the minimum bandwidth pulse which will have this nice property for us is the so-called sync pulse, right? That is, if we are transmitting a symbol every t0 seconds, we need to have a bandwidth only of f0/2 hertz, right? And then this sync pulse, that is the Fourier transform of this spectrum, exhibits those regularly spaced zeros which we are looking for. The response is maximum at t equal to 0 and goes through 0 crossings every t0 seconds. And that is a point at which the next response will build up for the next symbol, but it will not see any contribution from the previously transmitted pulse. Alright? So this is what we discussed last time briefly. The practical problems that we try to appreciate let me just summarize that. The sync pulse we found decays too slowly for us. Its decay rate is only 1 by t. Its side lobes are too large, and that it has a large slope at the zero crossings, right? Now, what is the significance of these three properties of a sync pulse in reference to our requirement? All these three things make the sync pulse very, very sensitive to timing errors that might be present. If we are not sampling the pulses at the right instance, if there is a timing error due to either a clock drift at the transmitter or a clock drift at the receiver, or perhaps due to some timing jitter that has come about somewhere, then the sync pulse will exhibit fairly large intersymbol interference. A slight disorientation in time adjustment either at the transmitter or at the receiver will make the sync pulse again give the same problems that we are trying to avoid in the first place. Okay? And this is essentially coming about because of sharp discontinuities which are present in the spectrum of the sync pulse. There is a sudden fall from 1 to 0 in the spectrum, which is not desirable. And the question that we posed at the end of the last class was, can we find a pulse PT that satisfies the Nyquist criterion but decays much faster than that? And what we said was, perhaps it will be possible to do so, and the answer in fact is yes, provided we are ready to use a bandwidth more than the Nyquist bandwidth, more than the minimum required for transmitting at f0. The minimum required is f0 by 2, but if we agree to use a bandwidth which is greater than f0 by 2, typically some k times f0 where k lies between half and 1, it is possible to obtain a pulse shape which is more perturbation tolerant than the sync pulse is. Okay, so that was a quick revision of what we did last time. Any questions on that? Yes, please.
So in the Nyquist criterion which we studied earlier,
yes,
where it said that to transfer let's say bandwidth of W, the minimum sampling rate we require is let's say 2f. For W we need is 2W.
Say that again.
The Nyquist criterion which we had stated earlier.
The minimum bandwidth required is f0 by 2 to transmit at a rate of f0 symbols per second.
Now out here, sir, we have signals.
Yes.
Even if the sampling rate is f0, then as we said the minimum bandwidth is W, but the bandwidth can also be more than W.
No, what is W? W is f0 by 2.
Yeah.
That's right.
I'm trying, sir, what we've done right now.
Yes, bandwidth can be more than
W.
W.
Nyquist criterion which we had done.
Mm-hmm.
So that's what I'm not being able to do. Because out there we said that if the sampling rate is f0,
yes,
then the maximum bandwidth that we get transferred is f0 by 2.
no, the minimum bandwidth that we need to do that properly is f0 by 2. We can use more bandwidth than that. That's precisely what we are saying now. We are now going to look for solutions which use more bandwidth, because as we tried to appreciate last time, we can find an infinite number of pulses which will satisfy the Nyquist criterion. Out of all this infinite number of pulses, only one pulse will have the smallest possible bandwidth, right? And that is the Nyquist bandwidth, and that pulse shape is the sync pulse. Now we are looking for other pulse shapes which will satisfy the same criterion, but which will try to use more bandwidth so as to introduce certain desirable properties, other desirable properties in the pulse shape. Not only the criterion itself, but other properties like fast decay of the pulse with time as we go away from t equal to 0. Does that answer your question? Is it clear now? Okay. Anybody else has any other problem? Okay. So then we proceed further from here. Let us see how we can show that this indeed can be done. That is, by using up more bandwidth, by allowing the decay not to be, by allowing the fall in the spectrum not to be sudden but gradual, we can introduce these desirable properties in the pulse shape.
If we use the sync pulse,
yes.
how do you generate it?
We'll discuss that separately. there are many methods of generating or realizing a filter with a given impulse response, right? We can use any of those methods. We can use passive methods as well as active methods. We can use digital signal processors for that matter. So generation of those pulse shape is something perhaps I will spend some time on separately, right? Because we'll see that a number of different kinds of pulse shapes may need to be generated, and I'll have a consolidated discussion of all of them together. Okay. Now, what we'll do is recall that our Nyquist criterion requires that our PT be equal to 1 for t equal to 0 and 0 for t equal to plus minus n t0, right? For n not equal to 0, of course. Let us say this PT has a Fourier transform p omega, and let us say that the spectrum of p omega is now not constrained between 0 and omega 0 by 2, but is allowed to spill over beyond it. Let's say it's somewhere the bandwidth extends to some point now between omega 0 by 2 and omega 0. Of course, the total band will be between 0 to whatever extra bandwidth we are using up. But our cutoff point now lies in this region rather than omega 0 by 2. Right? That's the essential change. We are now permitting p omega to have a cutoff beyond omega 0 by 2. Alright? I think I'll show a picture of a possible situation. Here is a possible p omega with this kind of a property. That is, your cutoff is no longer at omega 0 by 2, it's beyond it. It's between omega 0 by 2 and omega 0. Right? And of course, instead of a sharp sudden fall in the spectrum at omega 0 by 2, we now have a gradual roll off. Right? A smooth roll off. Now, for such a spectrum, what we like to do is satisfy this property. What we are going to do is, at the receiver, we are going to sample PT every t0 seconds, right? That is how we are going to look at what the values are. Let us say PT is sampled by a sequence of impulses, sampled every t0 seconds, by unit impulses, right? What that means is the sampling process will consist of multiplying PT with an impulse train of this kind. All right? Is that okay? And by requirement, this sample impulse, this sample pulse, after it has been sampled by this impulse train, should be equal to an impulse itself, because we would like it to be non-zero only at t equal to 0 and 0 at all other sampling instants. That means that sample sequence that we have got is also an impulse sequence by itself. So the Nyquist criterion requirement can also be put in the form of this simple equation. This should be equal to delta t. Why t0?
P0 is 1.
Oh, okay. Assuming P0 is already 1. You are right. Fine? Okay. So let's start with this equation again. Let's take the Fourier transform of both sides of this equation. This is a product in time domain, so we will get a convolution in the frequency domain, and the Fourier transform of each impulse is e to the power minus this should be nt0, j omega nt0, and this of course is equal to 1. There will also be, now again if you remember, we had obtained, or we have been using a formula which relates a summation of this kind with a summation of impulses, right, which is equal to, that's a Poisson sum formula for you, delta omega minus n omega 0. Or if we convolve p omega with each of these individual impulse functions now in the frequency domain, what we really get is this requirement, this criterion. It should be 1 by T0. What is the result of convolving p omega with each of these impulses? A function p omega shifted to n omega 0 with its center at n omega 0, and all these shifted functions added up together from n equal to minus infinity to plus infinity. That should be equal to 1. What does it mean? Any pulse shape pt whose Fourier transform p omega satisfies this would obviously satisfy this, right? We have in fact derived this condition from our required condition. So we have obtained a corresponding condition in the frequency domain now. Let's look at this condition by means of a picture.
So here PT is the actual signal transmitted or received.
Okay, and this is what I tried to recapitulate for you at the beginning of today's class. PT is the impulse response of the model for the total communication system, which consists of the transmitting filter, pulse shaping filter, the channel, and the receiving filter. Alright? So it's not either at the transmitter or at the receiver, it's a really combination of everything. We have a separate job to do afterwards as to how to realize this overall PT into the transmitter and receiver separately. What part of it should be realized at the transmitter and how it should be realized at the receiver, so that all three combined together gives you the required PT. But that's a separate problem, and we'll look at it separately when the time comes. Okay? At the moment we are just trying to design what PT should be like, right? And what we are now saying is that our PT by the Nyquist criterion requirement should satisfy this condition in the frequency domain. Is that okay? Understood? And can you picture this condition yourself in your minds? Basically you have your p omega which was restricted to 0 and some cutoff frequency between omega 0 by 2 and omega 0. Now you are replicating that spectrum around omega 0, around 2 omega 0, among 3 omega 0, similarly around minus omega 0, minus 2 omega 0, and so on. By replicating or repeating this spectrum over the entire frequency axis and then summing over all these functions, you must get a constant value. That's the picture that I would like you to have in your mind before I show the picture to you, which is like this. Right? This is your p omega in the baseband, which you are now replicating around omega 0 and minus omega 0, then 2 omega 0 and minus 2 omega 0, and so on. You're repeating this function or replicating this function again and again. And what we like to do, what the criterion tells us is that the sum of all these functions should be a constant equal to T0. Right? So if we design this baseband spectrum p omega, no matter whether it is restricted to just the Nyquist bandwidth or whether it spills outside the Nyquist bandwidth, as long as this criterion is satisfied, we are guaranteed to have a pulse shape PT which satisfies our requirements. This is the important point to understand. Okay? Any questions on that? Obviously the sinc pulse function that we have used earlier also satisfies this criterion. Why? Because in that case this was a brick wall characteristic, and this replication would simply put those brick wall functions side by side with respect to each other, and you will anyway get a constant function, right? So that was a special case of this more general result. Okay, so now we have a possibility of a whole lot of functions which can be the right kind of pulses to use, as long as that function has a p omega which satisfies this criterion, we are through. Okay. Now let us restrict our attention to those functions for which the cutoff lies between omega 0 by 2 and omega 0, right? And let us restrict our attention in that case only to the frequency band between 0 to omega 0, because if our function is like that, has a cutoff up to here, then if we are reasonably sure that it is going to be constant in this interval, because only 3 functions will come to the picture in this interval then. Which one? P omega, then P omega minus omega 0 and P omega plus omega 0, right? Because only these 3 functions will contribute to the sum in this interval, in the interval between minus omega 0 to plus omega 0. If these 3 functions when added together give rise to a constant value in this region, we will be assured that the same will also hold for the rest of the frequency domain. Okay? So therefore let us restrict ourselves now to a p omega of this kind rather than general p omega, and then we can write for 0 between for omega between 0 and omega 0, p omega, in fact between this range only 2 functions come to the picture, p omega and p omega minus omega 0. This should be equal to T0. Okay. So the condition becomes even simpler here for these kind of functions. Instead of having to work with an infinite summation, I only have to work with 2 terms in the summation. Let me now define a variable x which is related to variable omega through this. The motivation being, x will essentially denote, suppose I choose any point omega on the axis, x simply denotes the distance of it from omega 0 by 2. X can be both positive as well as negative. So depending on if omega is less than omega 0 by 2, x will be negative. If it is more, it will be positive. So I am defining a new variable in the frequency domain which is related to omega through this relation. And then we can put this condition in this form, x plus omega 0 by 2, and here it will become this minus omega 0, which will give you x minus omega 0 by 2 is equal to T0. And this limit I will now put in terms of x, magnitude of x less than omega 0 by 2. Okay? Please stop me if there is a problem. Assuming that our pulse shape is real, which is the case over here, you know, for real signals the Fourier transform satisfies this condition. P minus omega is equal to P star omega, right, for real signals. Okay, then we can write the same condition as P omega 0 by 2 plus x plus P conjugate omega 0 by 2 minus x. So first I have taken the negative of this so as to write P conjugate, and then you get this for x in this range. Any questions with the math so far? All right. Now let us make our life still simpler by saying that the spectrum is also real. It is not really a very big restriction, provided we are ready to work with zero phase and linear phase functions in frequency domain. We can later, if you want, permit p omega to have a linear phase function which will correspond to a constant delay. But to start with, let's say even p omega is real, that the frequency, the spectrum of the pulse is also real, which only means that the, for example, the sinc function that we discussed earlier will have a real spectrum, right? In fact, any symmetric pulse of that kind will have a real spectrum, right? So let's say we are having pulses of that kind. So in that case, we don't even have to worry about this complex conjugation, and we can say that our magnitude function should satisfy this required property. Have you come across this property ever before in some other context?
Vestigial.
Very good. So you remember that from your previous course. Okay. And pictorially, what that means is that we have what is called vestigial symmetry around omega 0 by 2. Okay, that is our function p omega, or magnitude of p omega, should have vestigial symmetry around omega 0 by 2. That is, if I were to fold this portion of the spectrum back into this region between 0 to omega 0 by 2 by just carrying out a folding operation at this point, then this function and this function should add up to a constant value. That is vestigial symmetry, right? And that is precisely what this states over here, right? This condition. You can please, if you want, copy this picture, and in the meantime, if you have a point to discuss, please let me know. So this is a vestigial symmetry condition. Which you must have discussed when you discuss vestigial sideband modulation in analog modulation systems, right? This is a requirement for vestigial sideband filters, right? Now here is the notation. Omega 0 by 2 is the Nyquist frequency. X is this new variable we have introduced, and omega x denotes the region over which we are allowing this function to have a roll off, right? And obviously the function has a bandwidth, exhibits a bandwidth which is greater than omega 0 by 2 by an amount equal to omega x. So omega x is also called the excess bandwidth that we are using up now, right? Excess over and above the minimum Nyquist bandwidth that we could have used, right? So omega x is excess bandwidth, and this is the meaning of vestigial symmetry. For example, if at the point x this value is alpha, then this value is alpha on this side. That is the meaning of vestigial symmetry. Let me also define a factor R here, which is known by the name of roll-off factor, and it is defined as equal to the ratio of the excess bandwidth over the Nyquist frequency, which is omega 0 by 2. So in terms of this roll-off factor, can I remove this now? Is there anything else that you want to look at here? Okay. Then your bandwidth of this pulse will now be given by f0 by 2 into 1 plus r. f0 by 2 is the Nyquist bandwidth, and this is the additional bandwidth that you are using up, r times f0 by 2. So that was a result that we wanted to show in the first place, that if we use up a bandwidth equal to kf0, where k lies between half and 1, right, which is precisely the situation here, 1 plus r by 2 will lie between half and 1, then we can have other pulse shapes which will perhaps be better suited. We still haven't seen that aspect. Whether these pulses will be better than the sync pulse or not is something we still have to try to appreciate. But at least we now have pulse shapes other than just the sync pulse available to us, a whole lot of them. As long as you have a p omega which has this kind of a shape, we are guaranteed to have the Nyquist criterion satisfied, and we can obviously construct many such functions. Okay.
So
Yes, please.
but an assumption is in this that you say that the signal in any pulse is also real in time and real in the frequency domain.
That's not a very big assumption, because any symmetric pulse shape around 0 will have that kind of a property. Symmetry in time will give you reality of the spectrum, right?
So the moment we say symmetry in time, it's not a real time signal. Like it's not in the negative time. We're saying it exists.
No. When I said real pulse, what I really meant was real valued pulse. That is, the function pt is real valued. It's not a complex valued function. Okay. Of course, it can have extent both in positive time as well as negative time. I didn't mean real in the sense of not using the negative time. Okay. It was being strictly used in a mathematical sense. Real valued function. pt is a real valued function. Okay. So I hope that confusion is not there. Similarly, when I say p omega is real, what I really mean is it's a real valued function.
Sir, what significance of the pulse existing in the negative time?
Well, strictly speaking, such a pulse shape is not truly realizable, but any such pulse can be always realized by introducing a sufficient amount of delay, right? I'll discuss these issues separately, right? And usually any communication channel will have a certain amount of delay associated with it. So at any point in time, you will not only see what the response to the channel due to the past, but in some sense also response to the future with respect to that time instant. Not the true future, of course, but future at the transmitter, because receiver and transmitter are separated by some delay, right? So you will see some future corresponding to the transmitter at time t, also at some time t minus td at the receiver, right? So we will discuss those issues a bit separately, because that will mix up the issues. Anything else? Okay. Now let us see some typical, excuse me, yeah. Now what we have to really decide is how to choose this pulse spectrum shape, right, so as to obtain some desirable property. To some extent, the fact that you are shaping it like this also is guaranteeing us certain nice desirable properties as such, because we have come out of the sharp fall and we now have a gradual roll off. Remember, the time frequency properties of signals are such that if one function, let's say if a function is very sharp in one domain, it will have a very slow decay in the other domain, right? We have avoided that situation here by not having a sharp fall. So to some extent we are guaranteed that we will have nice properties. The only other thing is whether we can come up with a nice mathematical function which will have this vestigial symmetry and also be very easy to realize or comparatively easy to realize. As it stands, truly speaking, these functions are not strictly realizable. I am not really going to go into that theory now, but if you see in the band between 0 to omega 0, which is perhaps of interest to us here, there is a region over which the function is absolutely 0. Such frequency domain functions are strictly speaking not completely realizable in time domain. They don't satisfy the causality condition required for real functions in the sense that one of our friends mentioned. But in fact, the condition that they don't satisfy, which is a well-known condition, I don't know whether you know about it or not, is known as Pali-Wiener condition, right? So these functions don't satisfy the Pali-Wiener condition. However, even if you don't know about it, let's not worry too much about it. However, the important thing is that because they have a nice shape, they can be approximately realized to a fairly good degree of approximation, fairly closely realized, right, by various methods of approximation, which we'll again go into separately at some other point in time. So I will not go into the realization issue here, but to say that if we have a reasonably smooth function, they'll be easy to realize. And one family of functions which have gained popularity in the digital communications literature for this purpose is a very well-known family. It's called the raised cosine family of spectra. And they satisfy this vestigial symmetry condition. Since I can't write it here, I'll write it on a separate sheet here. It's given by the following equation. P omega for the raised cosine family, which is a good family from a practical realization point of view, is given as follows. If you might notice, you could realize this function into essentially three parts. There is a constant part here, a zero part here, and a roll-off part here, right? So I'll specify each of these three parts separately. As far as the constant part is concerned, we can say it's equal to 1 for omega between omega 0 by 2 minus omega x, right? For values of omega whose magnitude is less than this, that corresponds to this interval here, right? Omega 0 by 2 minus omega x is this much from here to here, right? So in this interval of omega, it is constant. It is equal to 0 for omega greater than omega 0 by 2 plus omega x, and it has this roll-off shape in the remaining interval. Sine omega minus omega 0 by 2 into pi sorry, this is getting a bit cluttered, but I hope you can make it out. It is sine of omega minus omega 0 by 2 into pi upon 2 omega x, and the interval corresponding to this is omega minus omega 0 by 2 less than omega x. That is on either side of omega 0 by 2, which is less than omega x. Okay, and if you were to plot this function, basically that's what it looks like. I mean, part of a sine function, or you can think of some kind of a cosine function really, either this or this. You can have a whole lot of functions depending on what value of omega x you choose, right? Omega x is a parameter with us. If you remember, you could choose different values of omega x depending on how much excess bandwidth we are ready to use, right? The maximum we can go to in this scheme of things is omega x equal to omega 0 by 2, right? but we could use less than that if we wished. So we could therefore have a whole family of functions which satisfy this condition. This is a function corresponding to r equal to 0. That's the same good old brick wall function. That's a function corresponding to r equal to half, which will use an excess bandwidth equal to omega 0 by 4. That will go up to 3 omega 0 by 4. This is a 100% roll-off situation where you go up to omega 0. Right? Now, the important question is, what kind of pulse shapes do these various spectra have? Right? Okay, before I show the physical picture, I'll just do a bit of maths for that. It's a bit more involved to do it for the general case, to get the pulse shape for the general case. What I'll do is take it for the special case when r is equal to 1.
This is factor of 2 there in the denominator over here.
In the this equation here,
Because if you put omega equal to omega naught by 2,
yes,
then you get at 1 minus sine of pi by 2.
no, omega minus when omega is equal to omega naught by 2, this will be 0. So this is 0,
Okay, okay.
right? So this disappears altogether. You simply have half, right? Which is what we want. If this is 1, we like this to be equal to half, right? Try it out. You just have to plot this function to verify whether the picture conforms to this or not. Alright, so coming back to the maths, what I was saying was that we'll consider the case when r is equal to 1 to get the corresponding pulse shape. And for the rest, I'll just tell you what they are like. Yes, please. Speak
You
up.
haven't been considering the T0 factor.
T0 is very easy. I can multiply everything by T0.
Constant.
Okay. Yes, that's the point. I could have multiplied everything by T0. T0 here, T0 here. What that will do is, in fact, what I have shown here. Instead of PT having amplitude equal to 1, you'll have an amplitude corresponding to 1 by T0, right? Which is F0. Right? So it's a matter of putting the constant either here or here. It doesn't really qualitatively affect our argument. So consider the case for r equal to 1. That is, omega x becomes equal to omega 0 by 2. In this case, it's very easy to verify this statement that the same, in fact, I have to specify only one region now. There is only a roll-off region, right? There is no constant region, no zero value region. So, and in that region, if you make the substitution, that expression can be simplified, and that sine function becomes cosine function after simplification. And this is to indicate that the function exists only between 0 to omega 0. That's a rectangular function spread between minus omega 0 to plus omega 0, right? Which you can write as cosine square omega by 4f0 okay. This is the maths corresponding to the special case when r is equal to 1, and if you want to appreciate what PT is like for this case, you make use of this expression here. This is a rectangular function in the frequency domain with bandwidth omega 0, right? And here we have some additional terms. You can write this function, cosine function, as sum of two complex exponentials, right? So we'll really have three terms. One corresponding to the brick wall function alone, and two terms corresponding to brick wall functions multiplied by a complex exponential, right? Which will be like a delay operation in the time domain. So basically you can appreciate physically, I'll leave the details for you to check yourself. You can appreciate that PT will be essentially sum of 3 sinc functions, 3 sinc pulses, right? Like this. The basic sinc function corresponding to bandwidth f0, not f0 by 2. So it is 2 f0t here, right? Plus half of the same function but shifted by 1 plus half sinc 2f0t plus 1, right, which will, if you were to simplify that a little bit, you will get PT equals, I'll just give you the final result, skip a few steps. This will be the final result after simplifying that function. I'd like you to check that yourself, and if you have any problem, get back to me. So that's an exercise for you. And the plot of these functions looks like this. Whatever. Excuse me. Yeah, here it is. They all look like the same good old sinc pulse. In fact, this solid line I have drawn here is precisely the good old sinc pulse, right? That is, it has 0 crossings at T0, 2T0 and so on, multiples of T0. But what the effect of this roll off is, you can see here in these dotted lines, right? This one here corresponds to R equal to half. Of course, what we have just discussed is the case of R equal to 1. So what you will notice is, as you keep on increasing R, the value of R from 0 onwards towards 1, that is, as you keep on using more and more excess bandwidth, your side lobes decay very fast. In fact, for the case of R equal to 1, you can even mathematically see what is the rate at which they will decay. What is the rate? Asymptotically, let's say when T is very large, 1 upon T cube, because one factor of T comes from here and T square comes from here in the denominator. So the decay rate increases to proportional to 1 by T cube rather than 1 by T, which was the case of the sinc pulse. For the special case of R equal to 1, we even have 0 crossings midway between the desired 0 crossings. You will see that here. It may not have come out very well, but that's what this function is like here.
So only for R equal to, they will be for other values of R.
For R equal to 1, especially this property holds. For other values of R, they may or may not be. Roughly these additional 0 crossings, right? But in any case, that is not of much interest to us. What is really of interest to us is that we have the 0 crossings at these points, which will be available. Okay. So the net result is that, for continuing our discussion for the case of R equal to 1, our bandwidth will be equal to now f0, twice the minimum Nyquist bandwidth, which will be 0, the function will go through 0 crossings not only at plus minus nt0, but also midpoints of these intervals. Which only means that they are decaying much faster. The side lobes are decaying very fast. In fact, the asymptotic decay rate is now 1 by t cube. So as a result of these facts, the effect is that our sensitivity to timing errors will be considerably reduced as compared with the sync pulse. In fact, you can see that the slope at zero crossings also cannot be very large, because the side lobes are smaller. In fact, for r equal to 1, from one zero crossing it has to come back to another zero crossing. So it cannot possibly have a very large slope here, right? Therefore, sensitivity to timing errors comes down. And as a result, this is also more closely realizable because you have a gradual roll-off. Now, it also has another advantage which we will discuss next time. This function, the raised cosine family of functions, they also satisfy another criterion that was put forward by Nyquist, which is known by the name of Nyquist's second criterion. For zero intersymbol interference. Now we'll look at that second criterion more closely next time, and in fact we'll see that it is related to something that we already discussed in the context of line coding. So then that was the case, duo binary signaling we discussed here. We will see that there is a relationship between spectral shaping of pulses and line coding that we discussed earlier. Okay, I think this is a good stopping point for us today. If you have any questions.
So the second criterion is regarding
ISI.
Again, another criterion for intersymbol interference removal, but enabling us to double the bandwidth, double the data rate at the same bandwidth. Okay.